So hello and welcome to another one of our hypermill webinars. My name is Simon Docker, Sales Manager for OpenMind Technologies, and shortly I'll pass you over to one of my colleagues, Joshua Harper, who is one of the application engineers at OpenMind. So in today's webinar, we'll be focusing on 3-axis milling and how you can improve your quality and cycle times using hypermill. Now, I think it's safe to say that everyone knows and has come to respect the capabilities of hypermill when it comes to 5-axis machining. But as 3-axis machining predominantly equates to around 80% of most customers' daily machining duties, then we thought we should pay special attention to this, as the 3-axis cycles are more widely used than full 5-axis cycles. So now, as I've mentioned, hypermill is respected and highly regarded for its 5-axis cycles and capabilities. But let's not forget that the majority of 5-axis cycles are just an evolution of our 3-axis cycles. So the benefits that you see in the 5-axis cycles exist in the 3-axis cycles also. And moving on to the agenda for today's webinar, we'll be taking a look at stock management and the auto trim to stock function, smooth overlap blending, intelligent and automatic lead in and lead out moves, optimized roughing, automatic surface extension, high precision machining, and fast cycle time calculation. So the first thing, stock management, it's a really important feature for any CAM system, not only to reduce air moves, but for collision prevention also. Creating a stock chain within hypermill is really easy and powerful, and once the stock is created, it's referenced against the toolpath, but stored outside of the session. Now, the benefit of this is that the speed and performance, especially when working on a project with lots of models, is not affected. hypermill also has the ability to trim toolpaths that are remaining stock material. So this reduces airtime cutting and therefore faster cycle times on the machine. Okay, so why are the cycle times so fast in hypermill? Well, when the cycle is calculated, it stores the project data. So all NC files, stock and reference data are all stored in a project, but referenced to the hypermill project. And the benefit of this is that the speed and performance is not affected by model size or project size, regardless of the number of toolpaths in the project. So really, whether you have one toolpath or 300 toolpaths in the project, the performance will not appear any slower. Lead in and lead out moves, or macros as they're known in hypermill, these are really useful to reduce dwell marks where the tool enters and exits the part. You can set the parameters and type of lead moves manually in hypermill, but there's an automatic option that's used by probably 95% of the hypermill user base, so it's really not a necessity to set these manually. The model geometry is analysed before it automatically decides on the most efficient lead in and lead out move to use. There's also an overlapping option to prevent dwell marks if the tool was to enter and exit at the same point. So by overlapping and then sloping away from the part ensures that the part's free of dwell marks, leaving you with a perfect surface finish. So I'll pass you now over to Josh, who will take you through this.
Hello, thank you, Simon, for that. Yeah, I plan to take you through a short demonstration through what has just been mentioned. Just get the part showing. So what I'm going to begin with is a stock chaining scenario. Okay, stock is very important. One, it's defining the machining area, but secondly, it's allowing us to optimize toolpaths to the shortest possible machining movements. The first cycle that I've got showing here, I've just used optimized roughing, and I'm starting with a stock block covering the area. Press and calculate on this. It's using all my cores. It's a multi-core cycle, so we should get a quick calculation for this rather large model. Now, after this main roughing strategy, rest machining is going to need taking place. I have cycles after, and a nice simple way in order for those cycles to be referenced to the stock before is by simply highlighting the cycles, right click, and I can create what's called a stock chain. Now, what the stock chain does is automatically load in the stock from the first cycle into the next and sequentially through however many cycles you select. So now my second cycle is linked to the first cycle. The second cycle now knows exactly what stock is left over, what rest material there is. So upon calculation of my second cycle, it has now managed to optimize itself and trim itself to the shape and only the stock left over from the first cycle. I get a nice window down here, which is showing the stocks that the cycle is using and what it's producing. So I can do a comparison between the two. I can see, okay, that's the stock it was dealing with. That's the stock it's produced. And as I say, you can do this for any number of cycles. Rest machining. Our stock model tree is available and I can view it at any time. And you can even export these stock models. For instance, if you have a metrology department, you can actually export stock models so you can do a comparison between in-process workpiecing on a CMM and also, you know, what's live on your CAM system. You can do a comparison between what's being produced and what's supposedly. Simon also mentioned trim to stock. Now, 3D cycles such as optimized roughing, arbitrary stock, roughing cycles, they automatically trim to stock. But it doesn't stop there. Our 3D and 2D cycles also have the ability, because you might not just want to trim to stock when you're roughing, you might want to trim to stock when you're finishing all as well. So here I have a scenario where I've got a contour milling profiling around this shape. But let's consider that the stock scenario is the full stock block. And at this point, the engagement move and the cutting, not only is it plunging through stock, you know, remembering that this is a 2D cycle, it's also going to be producing full slots. Now, a nice function, certainly in contour milling and various other cycles that contain this trim to stock, is that you can actually offset this toolpath. If I offset it by 50 and press calculate, you can now see it's offset that profile shape by 50 mil all the way around. And what it's done is produce a lot of air cut. In a way, I've now removed the full slotting, but now suffering with air cut. But with tick box exercises, I can actually trim this back to the stock model and remove all of the air cuts. So all I've done there is turn on trim to stock and select the stock model in which I want to trim it to. And now you can see all the air moves are now replaced with G0 to the next point of cut. Tick box exercises, super quick, super easy. We also have a solution in a lot of the cycles whereby the lead in and lead out move, the macros, the engage and the retract, these are becoming more and more automated. We have a cycle here, which is currently set up on a manual macro. So when I calculate this, I have to produce a quarter circle radius coming in and out of the part. And you know, it's extra clicking time. Okay, I can see here, looking from the top, I've created this, but it's time and it's effort, and you have to think about it. More and more of our cycles now are becoming automatic in their macro. So you can see on this cycle, we have auto mode and manual mode. The previous cycle was manual. This is auto. When I press calculate here, it actually adapts itself and is checking against the model geometry to form a macro local and dependent to the area that it's machining. So when my macro is in the open area and not up against the model, I can see a nice tangential entry onto the material. When I'm against material, I can now see it started to roll on, and it's adapted as it's gone down. Now it works off formulas as well. The internal engine works off formulas. So what this means is no matter what size tool I use, I get a common result dependent on the size of the tool. It's formula based. The smaller the tool, the smaller the macro. As I say, more and more cycles are becoming automated in this. I now don't have to worry when I'm programming. I just worry at how it's cutting. The entry and exit is managed by hypermill. I think that's the first section complete. I'm going to pass back over to Simon.
Okay, so thank you, Josh. I'm just going to go back one slide. Apologies. Okay, so we all know that, excuse me, trochoidal roughing, or max roughing, as it's known in hypermill, has really been around for a number of years now, especially within hypermill, and it's a very good method for machining hard metals with carbide tools using the full depth of the flute. Hypermill regulates the step over and feed rate to maintain a constant rate on the tool, and it's really a very efficient cycle. But if we look at some of the more innovative cycles that OpenMind have developed, one, for example, is 3D optimized roughing. Now, as I say, it's a combination. It's developed by OpenMind, but it's a combination of strategies to maximize the efficiency of machining different types of materials. And one of the options is adaptive pocket machining, where hypermill fits pockets optimally into the area to be rough machined. And this really means that as much of the area as possible is machined with linear and spiral machine movements, and therefore maintain a high feed rate. Now, the planar levels are automatically detected and compensated for also, so it automatically calculating the step downs when it finds these planar levels. So over to you, Josh.
Yeah, thanks, Simon. Okay, so on to the second part now. So hopefully, yeah, a bit more of a prismatic part, real world situation here. And optimized roughing is the key topic. Optimized roughing is actually one of my favorite cycles. I think it's so easy to use and yet so powerful. It has several strategies inside, ranging from the traditional or conventional contour parallel type strategy that you see in roughing cycles. But then, as Simon said, we've got what we call adaptive pocket. Now, adaptive pocket is, as Simon said, splitting and analyzing the stock scenario at that given point and breaking it up into spirals or peeling off and pockets. Now, what it's focusing on is straight line movement. Straight line movement ensures that your machine is getting up to speed, okay? When we look at trapezoidal toolpaths, you're making good use of the flute length, okay? So tool life is going through the roof, for sure. But the dynamic that your machine requires is very high, okay? Certainly when we're looking at situations when machining aluminium, surface speed is going through the roof here. It's increasing. I've seen 9-10 meters a minute from tooling. Now, every movement is an arc movement in trapezoidal and requires heavy dynamics from the machine. You may not end up reaching the full potential. Whereas with optimized roughing, because everything is a straight line movement, certainly an adaptive pocket, and all it does is focus on detailing later. Okay, it removes the bulk of the material first, and then focuses on the detailing afterward. Ensures that the machine is kept free, straight line movement, and is able to reach feed rate. I have a scenario here. So let's just start the simulation a little bit differently. You see, it's the toolpath. It's slabbing or peeling off at the moment and working its way into the center. And what it's done is made sure it's removed the bulk of the material in straight line fashion, and it's focused on no detailing. You'll also notice that if I can just simulate to the end of the toolpath, everything is done with a fast feed reposition. And you can see at the end of this toolpath here, we've got large arc movements, okay? There's no dead stops. The tool is continuously moving, which is really aiding the machine to stay and maintain feed rate, okay? It's not having to slow down and then speed back up, slow down, speed back up. Everything is kept so fluid. And once the tool has left the material and it's performing this arc move and reposition, it's lifted off the material slightly, so you're not going to drag against any material that was left over. But also, this is done in what we call a fast feed move. So this is defined within the cycle. The repositions are fast feed. It doesn't release the machine into full G0 Fmax or rapid mode. It does fast feed, so it's controlled. Other areas where optimized roughing is great for, simple facing. Now, I've done a facing scenario here. I haven't got a machine model set up because this is 3-axis, but just showing maybe on a even 3+2 machines, we can machine multi-sided and have efficient slabbing off or facing operations. These moves that you can see are linking moves, so these are 5-axis linking moves, but we can focus on certain areas. And it's just lovely, clean toolpath. Now, adaptive pocket isn't just for maybe softer materials, is what you might have been getting from me earlier. It's not. Adaptive pocket can be used on harder materials as well. And we have specialized strategies for the harder materials. And when looking at roughing harder materials, you might be looking down the line of high feed machining, okay, high feed inserts, indexable cutting tools. Now, these are certainly becoming more prominent on the market. Lots of different geometries available, and the nice thing about hypermill is we handle all of them. Okay. Our optimized roughing allows us to use free tip geometry and it's a true calculation against that geometry. Okay, we do not have to fudge around with true cutting diameters. Okay, we define the cutting diameter. It's a 32 mil high feed cutter. That's what you call it, not true cutting diameter of 25 and having to fudge the figures. Now, what's nice about this as well is that we do get simulation of the true cutting diameter. So if I just bring this down. Now, something you're going to witness here, very important for your hard material machining. It's common knowledge that in hard materials, you should roll into cut, okay? Maintain cutting on one side of the cutter. This is one of the key factors in increasing tool life. This is the only tool path that actually has a roll engagement into cut. This is not an external macro before the cut. This is rolling into cut. It's an arc movement. Maintaining cutting on one side of the tool. Then it's slowly increasing into the full engagement. Now this tool path is a special tool path, and it's been developed to leave no material behind. Okay, we're looking at a full engagement here, and it actually works off a cusp height. Now, when we get to this corner scenario, the tool spikes off and then maintains cut direction. That spike is to ensure that no material wedge is left in the corner. If you were to simply roll around that edge, we would have a big triangular section of material. That spike is removing it. Not only that, it is also ensuring that when we're doing the arc move and changing direction, cutting is maintaining on the right-hand side of the tool. And it does it per corner. Now, what you're going to witness is actually what we call a cusp height left behind. Okay, so we can see this material left behind. So let me just dive into the cycle a moment. So to get high feed machining, we need to have adaptive pocket only turned on, and then you get a high feed machining option. Now this is controlled with a scallop height step over, full engagement into the material, the most stable form for the tool. We actually control the scallop height as a function. So I can say, okay, I want a scallop height of 0.5. The calculation says, okay, that is a 22.6 metric millimeter step over. Calculating. Nice and quick. Now this isn't just for facing, you can do cavity machining as well, and I'll show that shortly. So we should see a slightly shorter or smaller scallop height left behind here. Again, the lovely roll into cut. See, by producing a smaller scallop height, less material left behind. And you can see, you know, it goes unnoticed. First of all, I start pass over here on the right hand side. Once it's done its first pass, the tool is then retracting to the nearest start point. Okay, again, I'm back into cutting material already. I'm not having to retract up to a safe position, back down to the start position it used first of all. It's adapting all the way down for the best result. Now, we're looking at that rest material. It is of course possible in this cycle to remove that cusp height, and it's done simply by turning on plane level detection. And what this allows us to do is then define a scallop height that's left on part planes. So by turning on scallop height on part planes, setting as 0, giving it a quick calculation and watching the simulation. Same result, however, on the last pass, it will adapt the step over to ensure that it does not leave a scallop and you get a clean face left. Okay, so every part plane that it hits is going to ensure that it leaves it clean. Less rest machining required. So again, you can link these and increase productivity and keep the tool down on the job. That's not a problem. The next cycle is just looking at high feed machining, but you can see the same type of toolpath as adaptive pocket, but now it's focusing it on high feed. So you can, of course, sink into cavities, holes, pockets with this cycle in high feed, and you'll get a massive metal removal for your roughing operations. You can see it's adapted now itself to a pocket. It's constantly looking at the stock scenario to find out what's going to produce the best result here. Now, typically, you've seen a lot of toolpaths. Yes, high feed machining, you are reducing your step down drastically. However, these tools are doing millimeter plus per tooth metal removal rates, and it's incredible. Going to pass you over back to Simon. Hope you enjoyed that.
Thank you, Josh. Okay, so the next few slides and presentation part of the presentation will be focusing on certain areas that the mold and cavity guys out there will be really interested in, but I think it would really benefit all hypermill users. Now, the smooth overlap blending, for example, it's quite useful or quite common, I should say, when using different tools and strategies on a part, that you're left with a witness mark or transition marks or cusps at the connection point between the two tool paths. However, we've got an option called smooth overlap function within hypermill, where the tools paths are all intelligently overlapped onto its neighboring tool path to remove these transition marks. You can not only set the tool overlap, set the tool to overlap the tool path, but you also have the option for the tool to overlap and gradually lift off the part at the intersection point. So this is really all about quality and surface finish optimization. In this instance, we can see how the between the flat areas and the steep areas, we've had a really nice overlap there, and more of this will be shown by Josh in his presentation. Okay, so if there are any hypermill users watching this webinar today, then they will know that HyperCAD S, which is a surface and solid modeling CAD platform within hypermill, is completely integrated. But we've taken further steps to reduce programming times further by adding relevant CAD functionality directly into the form, or the GUI, as some people may call it, of each of the specific CAM cycles. Another area which is relatively new but really powerful is automatic surface extension function, to really control the tool engagement on a part and protect the edges of the part. Not only is this a really useful feature for the CAM programmer, it's now embedded within the strategy form in hypermill, so no additional CAD work is necessary as it's completely automatic. So again, this will massively reduce programming times. Another new, relatively new area within hypermill is high precision milling mode. Now, what is high precision milling mode? Well, if I flick to the next slide, it's a new projection method of creating a toolpath. I know a lot of our hypermill customers are using very small tolerances to achieve they're near mirror finishes, and this works fine, as we are known for our superior surface quality, but the calculation times will be longer the smaller the machining tolerance. The new method, however, called high precision surface mode, calculates the toolpath directly from the surface, and the end result is of much higher quality and only a slight increase in calculation. Now, there is without surface mode, and here's the same toolpath but with the high surface precision mode option ticked. Now here's an example of, I'm not sure in presentation mode, I'm not sure whether you'll be able to see the difference, but it certainly makes a big difference to the surface quality. So Josh, over to you.
Yeah, so just on the left-hand side, you can actually see some wave or streak marks going through the material. Now that is typically the facetation of the polyhedron underneath the surface. That's what we usually calculate to. But with the high precision surface mode, we're redistributing those points to the true surface. Now this is clever technology, because what that means for us is we're renowned for our safety. There's slight gaps in the hole and between surfaces and holes in the model. Typically the tool could dive through. We don't suffer that because we calculate to a polyhedron. But that could affect the surface quality. With the high precision surface mode, it redistributes the points, as I said, to the true surface. But if there are holes and gaps in the model, then the fail safe is still the polyhedron. Okay, very important. You still get absolute safety with the best surface quality. It's a win-win. I'm just going to take you through to the model. Now here, I've done cavity mold. Okay, this is more than likely where you're using these types of functions. Freeform surfaces, blending, overlapping surfaces. Now, I've set up a scenario whereby I've picked two cycles, Z level finishing and profile finishing. These are great for flat and steep area. Z level clearly for the steep. Now, we have a function inside these cycles called slope mode, which splits the toolpath at an intersection angle. Okay, this is to help maintain the strength of the cycle. Z level is great for steep area, profile finishing great for flat area. But there's always a crossover in the middle where one starts to fail. So with slope mode, it automatically and intelligently splits the toolpath at an angle that you define. And between the two toolpaths, you can very quickly start to blend or cover the areas where the other cycle missed. This is great. However, the boundary projection at this point is an approximation. Okay, tiny cusps and mismatches between the toolpath will occur at these intersection and join lines. The solution is tick box. Same cycle, but now with the function smooth overlap turned on. Now we've actually got two types of smooth overlap, but the first one ensures that it extends the toolpath into the adjoining surfaces and contacts the tool on the surface. So you're getting blending over and repeat cutting over the same surfaces from different directions to ensure that there's a nice blend. So we can see from the light bulbs on these two, we now get a blending between the toolpaths and the toolpath directions, a hashing as such, which is really nice. We're covering absolutely all areas now. But Simon said that we can do a smooth overlap, that allows us to blend off the surface. Now this, I've just focused on a small little patch of machining area down here. I've done some profile finishing. And this profile finishing is looking at machining underneath. I've split some surfaces. Okay, so there's some surfaces underneath, just to focus the working area. Now, it's concentrating on the large cylinder and then the radius. And I can see I've got a nice clean scanning toolpath. One on the other side. What we get is a join line in the middle. So in this instance, because it's the same toolpath being used, the smooth overlap function doesn't work here, okay? Because we're not requiring slope mode. Slope mode is when you're wanting to blend between the steep and flat areas. This can be used for the same toolpath, flat area to flat area. Now, I've actually done a scenario whereby I've machined the surfaces and turned on my smooth overlap at boundary. So what this does is you pick your milling area, your surfaces that you want to machine, and then you select the boundaries of those surfaces. And what it does is feather the toolpath off. Now, if I compare that now to these two cycles, which has the smooth overlap at boundary turned on, you can see a clear blend section and a feathering off on the toolpath. Now, if I can just turn on my clipping plane, you can see there's a clear intersection where the toolpaths are the same, but then the blue from the left-hand side starts to feather off vertically. Now, this distance and length can be controlled, okay? You've got the area length and the distance. The distance is the height. So what this means is typically you see mismatch like this when you're using different tools from different orientations. I've set up a scenario here whereby the machining taking place for the yellow surfaces, I have the tool leaning at an angle, and the blue is the tool leaning from a different angle. So these are typical areas where you would see a mismatch and blending and tool witness marks between toolpaths. With smooth overlap at boundary turned on, I can machine these areas, taking the cut off the center line of the tool, so you're going to improve your surface quality anyways, but also get perfect blending between orientations. Now, this is so important. Okay, this does not just apply to 3-axis. This is way far and beyond. When you're doing your super finishing, also in 5-axis, you know, this technology is helping to remove and get perfect blends between different tool types and different tool orientations. So the difference between smooth overlap at boundary and the general smooth overlap from slope machining smooth overlap is contacting the tool on the adjoining surface or toolpath area. Smooth overlap at boundary is looking at the same toolpath, but feathering off the surface at a distance and a height, so you get the blending between two of the same toolpath. The last thing is smooth, high precision surface mode. Okay. Now, Simon mentioned this. We've got some cycles here. I am just going to change the machining tolerance. So machining tolerance is changing the G1 length and the point distribution of the toolpath. Now, if I put this to 5 microns and calculate these toolpaths, Now we're fine machining tolerances like this. It just takes a moment. Now, what we're going to see is a point distribution over these toolpaths, and each one of these points is a line of code on your machine, a coordinate to get to. Now, in working with your machine, okay, high precision surface mode is creating a much better point distribution on your surfaces, and your machine with its smoothing code is splining through these points, ultimately creating a better surface finish. Now, if I just turn on Analyze Toolpath on here, I can actually turn on the point distribution. Now, you can sort of see it here. So on sidewalls and radiuses, you start getting different distribution points. Now, it's still, trust me, that's clean. Okay, that's a really good result, even without high precision surface mode. However, you may start to see facet or machining lines in certain areas. If we compare this to turning on high precision surface mode, it's just a tick box exercise. Turn it on and calculate. It shouldn't take too much longer to calculate this area. What we start to see is in the calculation window, adjustments and how many points it's treated, how many points from the tessellation, the polyhedron, compared to the true surface mode, it's adjusted in order to perform a better surface quality. Okay, so I've got quite a fine step over here. It's not doing too bad. 89% of points treated. This is really good. I'm just waiting for the profile finishing to blend into that area. Now I can actually look at this whilst it's calculating, it's not a problem. Turn on my point distribution. Now you can see point distribution massively increased. It's a code beast. But because we're able to hit these points, your machine now is reading these points and creating a smoother spline between. So we can go so far with the machine tolerance. Currently, I'm set to 5 micron machining tolerance with high precision surface mode. You can go sub-micron. If you've got a super dynamic machine, the latest Heidenhain controllers, they're good for 5 decimal places. Okay, and they are adjusting and splining the toolpath within that. So you can go down to a micron, even sub-micron machining. But realistically, okay, don't go going sub-micron if you've got a 30-year-old machine. Okay, it's not going to work as well as you think it will. Let's say the cycle and the machine, they go hand in hand. You should, if you do want an improvement in high precision machining and surface quality, then for sure, turn it on. But be realistic as to what your machine can handle. I think that that brings me to an end on those two. Simon, over to you.
Okay, so thank you, Josh. Thank you for that. Yes, okay, so that really concludes our webinar today. although I know that there is some questions that have come in, and although we don't have time to answer all of your questions that have come in this morning, we will of course answer those using the email address that you registered with, and we'll be very happy to speak to you about any other points that you've seen today, or about how hypermill in general. But there is one question that's come in that I'd like to answer whilst we still have the time, as it's quite important. And the question was, is hypermill available as a 3-axis option only, and is there a light version? Well, even the base version of hypermill offers 3+2-axis machining, and there are 2 versions of the 3-axis module available, and these are hypermill classic and hypermill expert. Now, even though the classic version may not contain some of the advanced 3-axis cycles that the expert version offers, it still contains a very comprehensive list of cycles, really built to reduce your cycle times and improve your surface finish, similar to what you've seen today. So yeah, it just leaves me to say thank you for attending, and although we've only had time just to show a preview of some of the many hypermill benefits that could help you to create better quality parts with faster cycle times, we'd be very happy to speak to you in more detail at the close of this webinar. So yeah, please contact us at Open Mind Technologies UK, and we'll ask one of our local sales managers to get in contact with you. So that just leaves me to say thank you, Josh. Thanks to all for attending, and goodbye.
Yeah, been a pleasure. Thank you, guys. Take care. Stay safe.